Okay, folks, we are lecturing Chapter 9, Section A, which is landing gear systems and maintenance. They talk about the different types of landing gear initially. And right here, we see two aircraft, okay? And I'm going to kind of do it a little different way, but that first column with landing gear types, I'm just going to summarize rather than try to talk about the picture at this time. What's a little crazy is that, when the Wright brothers developed their aircraft, there was really no landing gear, meaning any wheels. That they took off on a rail, they landed on skids, and that was all, okay? You got to realize weight of wheels and tires and brakes and all these things add a lot of weight to the aircraft. And especially in the early days, and even today, weight is a major consideration when we're building and designing an aircraft. So the Wright brothers was like, we don't need no stinking landing gear, As aircraft evolved, they came up and said, yeah, we need to be able to better move the aircraft on the ground and easier landing. So for takeoff and landing. And so they developed wheels for the landing gear, okay? Now, what's kind of crazy is early aircraft generally used what is known as pusher props. That is that the props were kind of in back of the main wing, not in front of the aircraft. And because of this design, they used what is known as a tricycle style landing gear. A tricycle standing landing gear is where we have a nose wheel and then two main wheels behind the nose wheel. Well, what evolved was then a little bit higher horsepower engine, but they realized that they needed a larger diameter prop to produce enough thrust. And because of the balance of the aircraft and that, they decided to move the engine forward to the nose with a very large diameter prop. The problem with this was that the prop was dangerously close to the ground. So to solve this problem, they created what is known as a tailwheel aircraft. And as the name implies, instead of having a nose wheel, we had two mains with a wheel at the tail of the aircraft, and the aircraft kind of sat on an angle with the tail down and the nose up. And the whole purpose for that was to keep clearance of the propeller from the ground, because the ground back then, where we took off, and that was what we refer to as unimproved, meaning that it was, farm fields and, nothing was paved and smoothed over and stuff like that. And so we really, the popularity of a tailwheel aircraft became so popular that it is actually referred to as a conventional geared aircraft. Although the tricycle was before the tailwheel overcame and became more popular and is known as a conventional gear. So why did we go back to a nose wheel aircraft? Well, as engine horsepower increased, the diameter of the propeller could be made smaller. Thus, we had better clearance between the propeller and the ground. Also, we started to improve our airports as far as, taxiways, runways, and such. And sorry about this, but I have a landscaper outside my office window weed eating and stuff, so it's kind of loud in here. Anyways, once they did that, they could move the tail wheel back to the nose to create the tricycle or nose wheel aircraft. The other problem that we had with the tail wheel aircraft is for taxiing, because when you're taxiing, and we'll go to it right now. Come on. Sorry. Okay, here we have a tailwheel aircraft. Now, A tailwheel aircraft, as seen in this DC-3, if you're the pilot and you're looking out, you're looking up. And we have this big nose in front of you, so you couldn't actually see what was in front of you as you were taxiing. So pilots that would be taxiing these aircraft, instead of going in a straight line, okay, what they would do is serpentine. They would actually like go to the right, and as they went to the right, they could look out the window to see if anything was in front of them. Then they would curl back, look through the other window. Yep, we're clear. And the aircraft basically serpentine back and forth to see where they were going. Okay, make sure that there was no obstruction in front of them. The other problem with a tailwheel aircraft is mainly during landing, but it can be other times, and that is a tailwheel aircraft has the main wheels and then the tail wheel. Okay, the center of gravity is somewhere in between, but it's after the main, forward of the tail wheel. Okay, now if we're going this way, okay, well, the problem is that when you come into land, for example, the brakes are on the main wheel. Well, the CG is where all the weight of the aircraft is trying to go forward. If, for example, then, and I'm going to kind of do it this way. So here's the main, here's the CG, okay? When it's trying to go forward, if the aircraft gets a little bit out of whack, the CG is going to try to fishtail you or spin you out. This is known as a ground loop. And that's because the wheels in front of the CG has more friction than the CG. So the CG tries to overcome. You may have done this before in a car. You know that you have the e-brake or the emergency brake, parking brake. A lot of people, their cars have a handle for that brake. Well, if you're making a turn, for example, if you pull up on the emergency brake, parking brake, understand that that only puts brakes to the rear wheels. Well, the rear wheels, if they start to slide, they lose traction, okay? And the front wheels still have traction. And if you're in a turn, you can see that you could lose control big time, meaning spin out. And in aviation, this is what's known as a ground loop. Is everybody clear with that? Keep in mind, with a tailwheel aircraft, also known as a conventional gear, they created the tailwheel aircraft to keep clearance of the propeller from the ground. One of the problems, and it's also known as a conventional gear. One of the problems with the tailwheel aircraft or conventional gear is that the CG is aft of the main wheels. By the CG being after the main wheels, the aircraft has a tendency to do what's called a ground loop. Okay. All right.
Okay.
All right. Now, so once, as I said, once the engines got stronger, we could use smaller propellers. Then we went to tricycle style landing gear, also known as a nose wheel aircraft. So now we have the vanes back here, we have a nose wheel up here, and the CG is now forward of the main wheels, but aft of the nose wheel. In this type of configuration, one, we can see now that the pilot can see better going forward so that they don't have to taxi in that serpentine motion. And because the CG is in front of the main wheels, during landing, if we lock up or, drag the brakes, meaning apply the brakes here, the CG still wants to go forward. So it keeps the vehicle going forward, meaning the aircraft. Okay. Good on that. Come on, Kayla. Where are you?
Sorry, I was muted. Yes, we're good.
Okay. At least do that and then I'll be happy. Get through a little quicker. All right. Are we good with that? All right. And so most aircraft are built with a nose wheel aircraft or tricycle gear. And also it's easier to make that aircraft nose wheel steerable than it is for the tail wheel. All right. So that was landing gear arrangement, tail wheel type, tricycle type landing gear. They talk about tandem landing gear. Tandem landing gear just means that one wheel is in front of the other, kind of in a straight line. Yes, you could see that, for example, on the main gear, there's a wheel, one in front of the other, that you can consider as tandem gear. Not a lot of aircraft have true tandem gear. If you know which the Harrier aircraft, it has a nose wheel, it has a body gear, but then out on the wings, it has small little gear that hang down just so that it doesn't tip over. Okay, nothing tandem gear, just keep in mind one foot in front of the other, if you will. So next they talk about fixed or retractable landing gear. That's the big question. And the answer is speed. Okay. Now this kind of goes back to the first picture and really is described well under landing gear types. Okay. Here's the thing. A fixed geared aircraft generally will weigh less than a retractable geared aircraft, because a retractable geared aircraft, you have to have, for example, something that can retract the gear. This could be a hydraulic system, an electric motor, hydraulics and stuff, and all this adds weight to the aircraft. Whereas a fixed gear is, relatively simple and thus weighs less. Well, here's the thing, and we kind of talked about it during the last class in assembly and rigging. We have two types of drag. We have parasitic drag and we have induced. Okay. Remember, parasitic drag is anything sticking out of that aircraft that hits air. The faster you go, the more parasitic drag we have. On the other hand, induced drag is created by lift. And so the heavier the aircraft is, the more induced drag we have. All right. Well, the parasitic drag curve looks like this. Okay. Here's speed of the aircraft, and here's the drag. Okay. As we increase speed, parasitic drag goes way up. Okay. Whereas, so this is parasitic drag. Induced drag actually goes and curls the opposite way. Because at very low speeds, what do we have to do? We have to increase our angle of attack to produce the lift. And as we increase angle of attack to produce more lift, we produce more induced drag. So a slow moving aircraft versus a fast moving aircraft. If the aircraft goes slow, okay, parasitic drag by having landing gear out, meaning fixed, okay, would be very low. And because the weight of the aircraft is lower, our induced drag would also be lower. Does that kind of make sense?
Yeah.
Okay, thank you. Now, if we had the same aircraft that moved slow, but made retractable geared aircraft, yeah, the parasitic drag would decrease somewhat, but it's already low. The induced drag would actually increase because the aircraft is heavier, thus having to increase the amount of lift that airplane is producing with angle of attack. So when we're in this range, we like to use a fixed geared aircraft. But as we go faster, what happens? The fixed geared aircraft doesn't, or doesn't, I don't want to say does not become, that doesn't sound right. It becomes less efficient because the parasitic drag increases significantly. But if we notice, the induced drag decreases because the faster we go, the lower angle of attack we can do. So kind of in this part forward, we like to use a retractable aircraft. Okay. And so that's basically it. You know, if the engineers are designing an aircraft that is designed to fly at low speeds, they generally will choose a fixed geared aircraft. Okay. If the aircraft is designed to go fast, they generally will, and there's always exceptions to rules, that they would choose a retractable geared aircraft.
Okay.
I think that it's kind of interesting that there's a Cessna 172, okay? And Cessna actually makes both versions, a fixed geared 172 and a 172 RG, which stands for retractable gear. And they fly right about 140 miles per hour, okay? Now, the fixed geared aircraft doesn't quite make it to 140, kind of it flies a little slower, but the retractable gear can go a little bit faster. And really because they're in that quandary area that, okay, which is the best? So they decide to make two versions and let the customer decide what they would like. Are we good with this?
Yeah.
Do wheel pants increase the aerodynamics, or is
Yes, they're there to reduce the parasitic drag. So, you know, if we have a really slow moving aircraft, I'll even say this, at our flight school, you know, Cessna 152s was our primary flight trainers in that. And we actually took off the wheel pants, okay, or the wheel skirts, however you want to call them. And the reason was because most of our aircraft were really, they weren't going anywhere except for doing, you know, practices, you know, in a teaching environment and doing a lot of touch and goes, you know, takeoff and landings.
So you want to be able to check the tires.
And so you got it. So it was, you know, it was for maintenance purposes. It saved a lot of time. And because they were not going to go much faster than 100 miles an hour, we weren't getting a lot of fuel savings and such. Now, for our cross-country aircraft, we did have wheel pants on it. We did actually quite a few things to that aircraft to save on fuel and to make that aircraft go a little bit faster. So it was wheel pants, it was lowering the angle of incidence on the wings, and it was also putting on what's called a cruise propeller rather than the climb props that we had for the primary flight trainers.
Yep.
So it was all these little things to modify that aircraft to have more of a specific role. Yeah. But yeah, wheel pants, and that's why like 172s and that they will generally have wheel pants on them just to reduce that parasitic drag. But then you increase the weight, so you increase the induced drag slightly. Are we good with that, John?
Yeah.
Yeah, teach you to ask another question. No. Okay. By the way, that was pages 2 and 3. Okay. On page 4, They go into shock absorbing and non-absorbing landing gear. Okay. For example, right here, this is kind of a picture of, well, they call, the streamlined wheel fairings and stuff like that. But this aircraft has what is known as a rigid landing gear. And the name rigid implies what it is. There is no shock absorbing device. It's just struts connected to an axle with a tire on it. These aircraft with rigid gear, very similar to the Mooney.
Mhm.
Ethan, is Ethan there? I don't see him right now. Oh, there he is. Yep, he's there. But these aircraft, they don't have any cushioning when you come into land, no shock absorbing device. Okay. These aircraft, generally are very lightweight. As you can see here, it's a wooden fabric aircraft. As the aircraft gets heavier, man, rigid gear can make you have a very, very hard landing, that's a bumpy and stuff. The Mooney aircraft, they have these rubber discs set in between metal plates that act as their shock absorbing device. And to be honest, they're not very forgiving. And when you're flying in one, when you come into land, you basically have to fly that aircraft onto the runway, because if you drop it, hit that ground, man, it's tough. All right. Now, a lot of fixed geared aircraft have what's known as a spring steel gear. The spring steel gear can be flat, like flat leaf springs of a car, or they can be a tubular spring steel landing gear. Okay. And tomorrow I'll be able to show you that on our aircraft. Okay. Because the 150s, some have flat steel, and then the 152 has the tubing, steel tubing. Okay. Now, something that I want to point out to you is, okay, we're looking at the landing gear. Can you see how the main wheels angle outward? Okay. This is known as a positive camber. Okay. When the wheels tilt outward, that's known as positive camber. If they were to tilt inward, that's known as a negative camber. Now, why are these wheels tilted out? Is because, well, spring steel. The spring is not being compressed at this time. When the weight of the aircraft gets onto the wheels, the springs will kind of bend outward, and the wheels will then go more vertical. Okay. If you land really hard, they could even point in for a second and then, get back to their normal weighted position. Okay. And that is spring steel. Now, okay, this one's pretty interesting. What's that?
What cub?
I didn't hear you.
Paper cub?
Yes. It does look like a Piper Cup, but without seeing the whole thing, can't guarantee. Okay. All right. So remember how I talked about the rigid gear? Figure there's two attachment points here. Okay. Now, if this was a rigid gear, it would be securely and could not move. But what they did to make it have some shock absorbing devices, these are hinges where a bolt goes through. So this can be pushed outward. It can hinge, go in and out on that hinge. Well, we can see then there's a cross member that goes to the other side. Then there's these black boots. Any idea what's inside the little black boots?
Maybe weights?
No? Ready for this?
Yeah. Rubber. Rubber bands.
Yep. Known as bungee
Bungee.
cords.
Okay.
Okay. They're bungee cords.
Okay.
And so there's actually, there's a metal rod here, metal rod, right? And then there's all these bungee cords wrapped around here. So when you come to land, well, when you're flying, the bungee cords pull the wheels kind of together. Okay.
Okay.
When you come into land, the wheels want to spread outwards and thus stretch out the bungee cords. And the bungee cords are the shock absorbing device.
Okay.
Yep. It's sorry to say, it's just that.
That's awesome.
Yeah. All right. Now, the most famous of all of landing gear shock absorbing device are what's known as shock struts. Okay. Shock struts are also known as oleo struts
Mhm.
or air oil struts. They are very similar to the shock absorber of your car. But here's the crazy thing. Ready? Your shock absorber of your car is much more complicated than our oleo strut.
Hmm.
And why is that? Well, most cars stay on the road all the time. And as you drive, that the surface of that road goes up and down and you hit potholes and you do all of those fun things, right? And so the shock absorber is, as the name implies, designed to absorb any of the road irregularities, okay? Whereas on an aircraft, we're basically always landing on improved runways, taxiways, divots and potholes are always taken care of. So we're basically landing and taking off on a smooth runway. And we're only doing this for very short periods of time. So it does not need to be very complicated, okay? And so with this strut, okay, hopefully you can see, we have this centerpiece here that is chrome looking, okay, and that is the piston, okay? Now, this part right here is, the proper name is called a torque link, but a lot of people call it the
Scissor link.
scissor links, okay?
Yeah.
And the scissor links basically keeps the wheel properly aligned, okay? Because if we didn't have these links, the piston, the wheel could spin 360 degrees.
Yeah,
And
you don't
thus,
want a landing.
this keeps the wheel in the proper position. And I'll talk more about the torque links eventually, but not right now. Okay. And then this little device is known as a shimmy
Master cylinder. Oh, the shimmy damper.
dampener. Okay. And just real quick, I'm going to talk about the shimmy dampener. Basically, it's a cylinder and it has a piston in it. And then there's the rod. So here's the one rod here, the same rod, but coming out the back. Okay. There's a piston in here. Okay. And this piston, though, has holes in it. So this is completely filled up with hydraulic fluid.
Okay.
Well, those holes allow the piston to move slowly forward and aft through the hydraulic fluid. Because remember, a liquid we cannot compress, okay? So it can only go forward and back as much as the holes will allow the fluid to transfer from the front to the back or back to the front.
Okay.
Well, the problem with many of the nose-geared aircraft is that we get, because of the geometry, we get what's called a shimmy. A shimmy is basically the nose wheel wanting to go to the left and to the right and vibrate kind of back and forth, And a shimmy, 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 and it can be kind of violent, okay?
Yeah.
Well, the shimmy dampener allows for the pilot to turn the nose wheel left and right slowly. But anytime this tries to move very, very quickly, the hydraulic fluid with the piston prevents any rapid movement. So it minimizes the shimmying of the nose wheel, and known as a shimmy dampener. Very, very simple device. And we will see it when we are in the shop doing projects. All
Okay.
right. Now, to get a little deeper into the oleo strut. And by the way, tomorrow is what we're going to be it's so much easier to show you the oleo strut in person. And tomorrow's main project is for the disassembly, inspection, and reassembly of the oleo strut. So,
This is just like a motorcycle.
oh yeah, yep, it's front strut of a motorcycle. You got it. Now, so here's the chrome piece that I showed you, and that is known as the piston. Okay, so I'm going to kind of try to redraw. So here we have the piston. Okay, now over the piston is the cylinder.
It's like a sleeve.
Yeah. Okay, so the piston can get pushed up and down. Okay, now on the inside, okay, we can see that we have this what's called a piston tube. Okay, it's right here. So we have this piston tube. I suck at drawing. It's so difficult sometimes. Wonder if I could grab this other thing. Anyways, I'm going to try. Inside, I'm going to just try to do it here. And if it doesn't work, I'm not going to beat myself up. We're going to see it tomorrow. Okay. Here's the thing. When this is fully extended, the red, which is the hydraulic fluid, is all down low. Okay. It's into this chamber. When we come into land, the piston is pushed up, but the fluid is kind of trapped here. But there's an orifice, an opening here. Okay. And that's what I did wrong. I drew that one wrong. Okay. Let me try this again. And let me make it bigger. All right. So now we have, this is what's called the orifice tube, and it kind of bulges out like this, but there's a hole here. Okay. The piston is here. Okay. And then we have O-rings that seal it. Okay.
Okay.
And this piece and this piece make a seal. Okay. Now, when it's fully extended, we have oil down here and we have a gas up here. Generally, we use nitrogen. Okay. Now, when this gets pushed up, the oil has to go and compress the nitrogen. So the oil actually has to flow through the small, what's known as the metering orifice. Okay. And it goes through the metering orifice, out holes of the metering tube. And now what's happening is the nitrogen is getting compressed, and we can compress a gas. And that is one, the opening here limits how quickly this can close. And then the nitrogen is giving the cushioning effect. Okay.
Okay.
One of the things that you need to remember is that when an aircraft is sitting on the ground, okay, and we will see like a little bit of an extension of the piston, what the aircraft is actually riding on is then the gas charge. The nitrogen is supporting the aircraft. Now, When we go to take off, the weight of the aircraft is no longer on the struts. And so the nitrogen can expand, pushing the oil back down, and the piston will extend. Okay. I know that this really doesn't make sense unless I can show you the stuff. All right. And tomorrow we're seeing it. So, okay. Now, this one, if the oleo strut is installed on a relatively light aircraft, okay. For example, the Cessna 150s, the ones that we're going to be taking apart, which is from a multi-engine aircraft, an Aztec/Apache, they're relatively light. And so all they need is a metering orifice. As an aircraft gets bigger and heavier, the problem is that when we come into land, if we only have a small orifice opening, the pressure can build up so great and not, flow past the orifice fast enough, and too much pressure could be built up. So they have what's known as a metering pin. How the metering pin works is this. So here's the metering orifice, and then the metering pin kind of tapers out like so. And the idea is this: when we're up in the air and no weight on the wheels, the metering orifice is fully open. Thus, when we come into land, there's a lot of fluid transfer that goes from the bottom to the top. But as the oleo strut gets compressed, the metering pin closes off, or starts to close off the metering orifice, so it restricts the amount of fluid that can transfer from the bottom to the top. So it slowly makes it harder to compress that strut. Are we good there?
Yeah.
Okay. Well, what happened was then they developed a problem, because the opposite happens when you take off. When you take off, the weight comes off. Initially, the oleo strut has a slow extension, but because the opening of the metering orifice is small, so it can only extend out slowly. But as it comes down, the metering orifice is opened up more and more, thus allowing more fluid to transfer at a faster rate. And so they would get what's known as a hammering blow. And it could actually blow out the strut from this cylinder, meaning the piston from the cylinder. So they added this top piece. So it's kind of like a double valve that expands out this way. Okay. And I know, and this is known as a snubber. What the snubber does is it allows the strut to fully go out or extend, but as it reaches its full extension, the snubber closes off the metering valve, metering orifice, or restricts the metering orifice, so there is no hammering blow and slows it down when it gets to full extension. If you're not fully aware of what I've just said, we will see it tomorrow.
Okay.
Good?
Yeah.
Okay. But, like I said, compared to shock absorbers of your car, especially you can have single acting, double acting, meaning controls that you can change the rate of compression or the rate of extension by the use of valvings and stuff like that. Some larger oleo struts have where this is, where the metering orifice kind of looks like that. There's actually a pressure plate here with springs on it. And then there's additional holes. That way, if the aircraft has an extremely hard landing, the pressure here builds up so much, but only has one passageway through the orifice valve, metering orifice, excuse me. there's additional holes. So when the pressure builds up, these are basically pressure reliefs that allows additional fluid to go from the bottom to the top chamber. And then the springs close it down and stuff like that. All right. I'm not really going to talk about servicing of shock struts because that's something that we will be talking about in class. And, you know, it's just much more efficient talking about it as we do our projects and such. Are we good with that?
Yeah.
Okay. I don't know. I'm going to see if I can find something real quick. Okay. I'm trying to find something. Uh, huh. I don't have it. Nope. All right. I'm not going to bother you with it. Okay. It's close enough for break, and this is a good time to take the break. We're going to come back. Yeah. Okay. We're going to resume the lecture starting at 8:30. All right. And then we're going into aircraft wheels. All right.
You said 8:30?
Yeah, 8:30.
Okay, see you in 10.
All right. Okay, I'm back. Um, yeah, as I'm trying to go through this, if there's things that I know we can do much more efficiently when we come into class, I'm just going to mention what it is and try to go through it as best that I can. But, you know, I will go through it definitely when we're in the shop. All right. To continue on then, we're talking about the aircraft wheels. And once again, what we have to understand is weight is such an important aspect of the aircraft. And sorry to say, when do we use the wheels? When we're on the ground, be it taxiing to take off, or when we come into land and then taxi back to the ramp. Okay. So it's a lot of weight, a lot of complexity. And we want to keep them as light as possible so that when we're flying around, we're just a lot of wasted fuel. Okay. So our wheels are not like automobile wheels. Okay. And what do I mean by that is they're actually multiple pieces. Okay. And of course, they don't kind of show that picture right away or at all. Okay. But our wheels come in 2 pieces minimally. Okay. Some actually are 3 pieces. So our aircraft wheels are bolted together. So we have a hub like so, right? And then the other piece goes like so. And the tire, of course, fits like that. And they're bolted together. Of course, they're not that close together. Anyways, and such. Now, some are 3-piece, where then you have the outside rims, and then you have the center, and then an inboard rim. Okay. Now, and I'm just going to talk about the 2-piece rims because those are the most prevalent out there. So we have a 2-piece rim. What they came up with is, hey, we need to be able to say or identify which rim is which. Okay. So they came up with the term the inboard and the outboard. Now, I think it's kind of funny because inboard, outboard doesn't necessarily mean in which way they are facing on the aircraft. Okay. So how can you identify the inboard and the outboard portion of the rim? Because if we look at this one, right, this is inboard. Okay. Well, you would say that's the inboard wheel half. Hey, but guess what? This half is this half. This half is that half. So the inboard wheel half, as our book talks about, can be identified by a couple things. One is that we have brakes. Okay. So if the wheel has brakes, they will have an attachment for the brakes. This many times is known as the disc drive slots. All right. Also, some aircraft have what's called what I just went blank. They're fuses. Hey, fusible plugs. Okay. They have what's known as fusible plugs. Okay. So if you're inspecting a wheel half and you see that there's an area for the brakes to go, or if it has fusible plugs, we know that's the inboard or identified as the inboard wheel half. The outboard wheel half is identified by the valve stem. Okay. And that's probably the easiest way to identify. The valve stem is where we add the air or the nitrogen, the gas to charge the tire. Okay. So outboard wheel halves have the valve stem. Okay. If it doesn't have a valve stem, we're dealing with the inboard wheel half. But they like, and you should know, the inboard wheel half many times will have brakes, or they will also have what's called a fusible plug. I'm just going to speak about the fusible plug right now since I brought it up. And you may be going, hey, what's a fusible plug? Well, here's the problem. Here we have a tire, right? And there's our rim. And now the problem is this. Here, let's say we're coming into land, the brakes catch on fire. And yes, that can actually happen because they can create a huge amount of heat, okay, when we go to stop. Well, that heat can heat up the gas that's inside the tire enough where the tire could actually blow up, okay, because of overpressurization. The idea is that on a fusible plug, okay, what it does is that the fusible plug has a low melting point metal, like I'll give you an example, like solder. Okay, it ain't solder, but it's a low melting point alloy that if the tire gets hot enough, that the low melting point slug in there will melt away so that air inside the tire can escape, but not rapidly decompress. And the purpose is so that, for example, an airplane comes into land. What we don't want is that tire to blow out and have a flat, okay? So as the temperature rises, the low melting point or the fusible plug, the center portion of the metal melts away, creating a calibrated leak. This prevents the tire from being overpressurized, but still keeps pressure in the tire so it doesn't rapidly deflate. Hopefully, then we can come to a complete stop with control of the aircraft. Now, once the aircraft has cooled or the tire has cooled and such, yes, the leak still occurs and that tire will go flat, okay? But the aircraft has landed safely, and that is what's known as a fusible plug. I will also mention, so I don't have to do it later, which I still will, is that when inspecting a fusible plugs on a rim, okay, many times there's more than one fusible plug on a rim. Well, if it shows any signs of deterioration or wear or melting, not only do you have to replace that fusible plug, but you have to replace the others that are in that wheel. Good. So the question is, when inspecting an aircraft, you find a worn fusible plug, what should you do? You replace all the fusible plugs within that wheel. All right. Now, so I'm just going to kind of go back real quick. All right. Inboard wheel half, how can you identify? You can identify it by brake installation or by fusible plugs. How can you identify the outboard wheel half? By the valve stem. When inspecting, you find fusible plugs to show wear. What do? The answer is to replace. Okay. Now, I'm going to kind of not go every paragraph by paragraph. I don't kind of like how they do. All right. So I'm going to say it in my own way. Okay. Let's say that your task is to remove, disassemble, and then inspect, clean, and then reassemble the wheel, okay, entire. So what do? Okay, we bring the aircraft in, and then we set up the jacks according to the maintenance manual. Now, we can then lift the aircraft or the wheel off the ground so it's, not bearing any weight. Now, prior to doing anything with the wheel, what we want to do is to then deflate the tire. remove the air pressure, okay? And the reason is this: the wheels are held on to the landing gear by a single axle nut, okay? Now, the two rim halves are held together by bolts. What has happened in the past and what could happen in the future is that the tie bolts that tie the two rims together can be damaged. Threads could be stripped, corrosion could have occurred. And really, the only thing that's holding the two rim halves together now is the axle nut. So these tires many times can have over 200 PSI of pressure in them. If you were to remove the axle nut while the tire was pressurized, that could actually put enough strain that the tie bolts let loose and the tire is now exploding into you, okay? Which is an extremely dangerous situation. So by deflating the tire, we are now safe to proceed without the fear of it exploding in our face. So depending upon the tire, we follow the maintenance manual. If, for example, the brakes are associated with that tire, we have to disconnect or do something with the brakes so that the tire is free to be removed. And that really depends on the type of braking system we have. Once that is taken care of, we want to remove the cotter key that is holding the axle nut in place and remove the axle nut. From there, we pull the tire off of the axle. Now, the next thing we want to do, and this is kind of a cheapy system, but we need to do what is called to break the bead seat area, okay? The tire, the inside that contacts the rim is known as the bead of the tire. And on the rim, it's called the bead seat. Well, those two will pretty much be stuck together. And prior to removing the tie bolts or even loosening the tie bolts, we need to break that loose so that we can facilitate removal of the rim from the tire. So we break the bead seat area. Now, what we do not ever do is pry against the rim. We don't take a screwdriver, we don't take a pry bar and put it between the rubber of the tire and the rim. You got to understand the rim is designed a specific way so that it's extremely lightweight. So many times the material's made out of aluminum or a magnesium alloy, okay? And if you try to pry on it, you could scratch it, you could break it, you could cause stress concentrations into it. So we never put any metal up against the rim and try to break the bead seat, okay? As you can see here, they're pushing down on the rubber portion of the tire to separate it from the rim itself. Now, once the bead has been broken, this is when we can then remove the tie bolts. Once the tie bolts are removed, we then can separate the two rim halves, okay? Now, once again, no real good pictures, okay? But, you know, not even that is a very good area, but it's the best that I have, okay? So what we want to then do is remove the bearings and inspect the bearings. I'll do that first because that's kind of what they're showing here. Okay, now, pretty much anything that you notice on a bearing, unless they look absolutely brand new, causes the bearings to be rejected. What they're showing here is that the bearings are basically two pieces. We have the roller bearing, such as these, right, which is a cone, and then we have what's called a race that the bearing rides along. many times you will see these black lines on the races or on the bearings themselves. Any discolorization or like what looks like little black lines, many times people refer to them as water spots. What that actually is what's known as intergranular corrosion. And there is no repair for it except for replacement. If you see a bearing that is discolored, such as this bearing right here, and this is what I was talking about being a cone bearing, okay, because it's, you know, cone shaped, but you can see the discolorization and a line here. Or if you see like different colors like blue and stuff, that indicates that the bearing has been overheated and thus has to be replaced. Now, when replacing a bearing, we can't just replace the bearing. We have to also replace the race. They are a matched set. Whenever removing the bearings, we always want to identify which is which, meaning the inboard or the outboard wheel half. Because if you mix them up, the bearings will fail in a very short period of time. Okay, so they're a match set, and when one or the other have to be replaced, you have to replace both, meaning the race and the bearing that it's associated with. Okay. Now, also here, this is what's called galling. A portion of the race has kind of flaked off, and that's galling. Totally bad, reject. You know, majority of the time, if the bearings have been used for any length of time, most of the time you will find that the bearings have to be replaced. Okay. I will discuss how to remove the race when we're doing this project as far as disassembly, reassembly of the tire and inspection. Okay. Now, for the rim itself, okay, the race and say the bearings are removed, the races are removed, and we're going to put new ones in. Okay. Anyways, we want to thoroughly clean the wheel itself or the rim. Okay. And then we need to do an inspection. Now, depending upon the aircraft and the weight of the aircraft determines what type of inspection must be done. But let's talk larger, the more complex. Okay. For the rim, okay, we have to do what's known as a non-destructive testing. Now, the most critical part of the rim is what's called the bead seat area, this kind of curled part, because think that the tire bead is pushing out against that area. So this is trying to get pushed this way and stretch this out. Because of that, this area has been pre-stressed to try to move inward, okay? It is so much pre-stressed inward that if there's a crack in the bead seat area, the pre-stress will close that crack where you would not be able to detect that crack with normal non-destructive testing, such as a dye penetrant. So you're not allowed to dye penetrate the bead seat area for a proper inspection. So what type of non-destructive testing do we do in this area? And it's known as eddy current. We do the eddy current inspection on the bead seat area because that would detect even the slightest crack or flaw within the bead seat area. Okay. The other area we normally use eddy current is in the bolt holes. Okay. Here we see the tie bolt. Okay. Now keep in mind the tie bolt is made out of steel, while the rim is made out of an aluminum alloy, maybe even magnesium alloy. Dissimilar metals happen to create corrosion. So there's a good possibility that we could have corrosion in this area. And so a eddy current inspection is generally done to the bolt holes. The bolts themselves get magnetic particle inspection. Okay. Also, many times they are measured for their length to determine if they've been stretched. Okay, so keep in mind what type of inspection is done to the bead seed area. Remember, it's eddy current. Okay, now, can you use dye penetrant in the bead seed area? And the answer is no. And the reason is because the pre-stressed bead seed area can prevent the dye from finding the crack or soaking into the crack, however you want to say it. Okay. Now, where we can use dye penetrant is what's known as the disc drive slots. This is what drives or turns the rotor disc on some aircraft. As you can see here, this has been dye penetrant. And right here, what's kind of funny is it's really dark and it looks like it's rounded. It's really not. For whatever reason, the cutout of the rim is square. And then these two fasteners hold that disc drive slot into place. Well, this is where the crack develops. Okay. So if you notice right here, there's a very faint line running this way. There's a very faint line running right there. Okay. And so you can use dye penetrant in the disc drive slot area on the rim to identify cracks. Okay. So we have the rim apart. We remove the bearings. We've inspected the bearings, right? We've done the non-destructive testing of the rim. Now it's time to put it back together. Okay. We grease the bearings. We put in the races, right? We then put the tire onto the rim. If it's a tube type tire, the tube is installed into the tire and then the rim is placed inside the tire. Okay. Couple of the other little things I'm going to discuss in class as far as how do we set up where the valve stem goes and stuff like that. But then we really just put it back together. And then later on, we'll talk about airing the tires and stuff like that. But then we install it on the aircraft. We do a proper inflation of the tire. Keep in mind, that's for another lecture. All right. I'm good on that part. Let's see, bearing inspection and talk about that. Balance, okay. You know, inspection of the rim. This one is all corroded up. Here is that fusible plug that I've talked about. It's really hard to tell, but there's a small little circle right there. That is the low melting point alloy that's there. Okay. All right. Any questions before I continue on?
No.
Okay. All right. Thank you for that. Kayla was a little bit slow there.
It was, my computer died. I just got it back on after the break.
Oh,
Sorry.
all right. Yeah. Okay. All right. So on page 9-11, we go into nose wheel steering systems. Now on small aircraft, when we were in assembly and rigging and we rigged the rudder, I showed you how the steering rods go from the rudder pedals to the nose wheel and where the little springs are and stuff, right? So on a small aircraft, basically the nose wheel for the nose wheel steering is connected to the rudder pedals so that when the pilot pushes on the left rudder pedal, it actually pulls the nose wheel to the left, push on the right, the nose wheel then pulls to the right, okay? When we get to larger aircraft, and what was always funny, and in the early days, I used to teach general. And yes, we had a runnable, operable Cessna 150 or 152. And I would have during ground ops, I would have the students taxi the aircraft. And what I loved about it was, people would put their hands on the yoke as it was the steering wheel. If I noticed that the person had no idea that there's rudder pedals, I would tell the person, okay, turn to the left. And let me share my camera. Oh, they're good. Okay, hello. All right, so I would be sitting there, I would have the person start the engine and stuff, then I'd be like, okay, let's go forward. They put in the throttle and they're holding the yoke like this, like it's a car, right? And it'd be like, okay, turn to the left. Well, I would see them. Okay, they would go like this to try to turn to the left. So as soon as I noticed that, I would push on the left rudder pedal and we would go now to the left.
You're teasing them.
Well, they don't know anything yet. Then I'd say, okay, go to the right. So they move the yoke to the right. So I push on the right rudder pedal. Now we're going to the right. Oh, okay, you're doing really good. Then as we were getting to the end, I'm like, okay, turn left. So they would go like this once again to go left. But this time, instead of me pushing on the left rudder pedal, I now push on the right rudder pedal. So what do? We're going to the right when they should be going to the left. And they're going, oh, and they're turning harder and harder and harder. And I'd turn it further and further. Like, what are you doing? Come on, we're going to crash. Yeah. And then finally, I would have to let them know. This does nothing. This rolls the aircraft. It operates the ailerons. Look, we got rudder pedals. So then when we would go back, then they would understand how to use the rudder pedals. Okay. On larger aircraft, like the 7.2 and such, commercial aircraft, the steering is no longer done by the rudder pedals because there is no mechanical linkage to the nose gear to move that left and right. It's all done by hydraulics. So instead of using your rudder pedals, you have the pilot and co-pilot has what's called a steering tiller, okay? And thus you can move the steering tiller forward and back. One is to go to the right, one is to go to the left, and that's how they steer the aircraft on the ground.
That's
Good.
cool. One time I was in a plane that had finger brakes.
Finger brakes, really?
Yeah, I forget what it was. I think it was one of those composite planes.
Huh. I don't know that one. That's kind of cool.
If I think of it, I'll tell you.
Yeah. Yeah. All right. Okay, so that's small aircraft, that's large aircraft. Hey, we now talk about the shimmy dampener. Hey, didn't we talk about the shimmy dampener already?
One of them.
Yep. Well, pretty much any shimmy dampener does the same thing. This one's a little different, okay? In that you notice that there's no rod coming out the back end.
Right.
It still has a piston in it, and that this is generally found like on Pipers and that. And what really sucks about them is this. With the other style, you can actually disassemble and replace the O-ring and do all the different things. Basically, you can rebuild them and service them. On these, they're non-serviceable, meaning that when they go bad, the only thing you can do is buy and replace the shimmy dampener. And sorry to say, they're not really cheap. Yeah. Okay. But we've talked about the shimmy dampener, and when we're out there, I will discuss how to service, if they're a serviceable one, I will demonstrate, or we'll talk about how to service it and such. All right. But as I said, they're designed to prevent the shimmying, the back and forth rapid motion of the nose wheel. Now, on large aircraft, let's see if there's, okay, there's the shimmy dampener again. There's the torque links. All right. Oh, okay. Ah, okay. Here's the nose wheel steering of a large aircraft. Oh, I didn't turn the page. That's why I didn't see it. Okay. And so here, what do we have? Okay. We have the steering cylinders, and generally there's going to be 2 on the nose gear, right? And so when you're moving the tiller or any other nose wheel selector valve, you know, could be by the rudder pedals, but most of the time it's by a tiller. And what does it do? It directs the hydraulic fluid to the proper actuator side to then move the nose to the right or to the left. Because we now have actuators on the nose gear, the nose gear actuators or steering cylinders also act as the shimmy dampeners. So they combine the name and call them steering dampers. Woo! That was fun and exciting. All right. All right. Where are we at now? There we go. Landing gear alignment, support and retraction. The wheel alignment, okay? And I hate how the book kind of goes, but all right, I'll use this one. Okay, wheel alignment, okay? 2 things we have wheel alignment. One, I've already kind of mentioned, and that's called the camber, okay? The camber is, here's the center line. You know what? I'm going to do toe in, toe out first. I think. Let me see which one that they talk about first. I'm going to do this one. All right. Here's the center line of the aircraft. Here's forward. Okay. Now, generally, we're going to be talking about the main wheels. Okay. And the main wheels, for all practical purposes, should run parallel to the longitudinal axis of the aircraft. If, for example, a wheel kind of points in, okay, we call that toe in. Okay. If the wheel has a tendency to point outward, that's called
Toe out.
toe out. Okay. Now, the FAA questions, they go, if you were to take a straight line and the tires would intersect in forward of the aircraft, is that toe in or toe out? And the answer is that's toed in. If the straight line of the tire goes or crosses the longitudinal axis behind the aircraft, that's known as toed out. Okay. I usually use the term point. Okay. So for a Bob question on a test, if I say, hey, if the wheel points in, that's toed in. If it points out, that's toed out. Understand?
Yeah.
Okay.
That's for
So
me.
how do we adjust toe in and toe out? Well, here we have what's called the torque links. The top torque link is connected to the cylinder of the oleo strut. The bottom part is connected to the piston. And remember, if this is disconnected, the piston could rotate 360 degrees. Well, this is what keeps the wheel properly aligned. So how we move or toe in and toe out is by adding washers in between the 2 connections of the torque links. Okay. Now, we add or remove washers to adjust toe in, toe out. Now, the hard thing is, for example, if over here is the center line of the aircraft, so this is the left main, if we add washers here, that would actually toe it in. where if we removed washers, it would then tow it out. It would be the opposite if the center line of the aircraft is here and this is the right main. If this was the right main, when I add washers here, that torque link would move this way, and thus the little tire would actually point outward, so it would tow it out. Whereas if I removed washers, it would pull it in and thus would be towed in. So there is no, hey, I add washers, it always will do this, okay? It depends upon the arrangement of the torque links and where that landing gear is associated, being the right main or the left main, okay? But how do we adjust the tow in, tow out? We do it by adding or removing washers between the torque links. Okay.
Mhm.
Now, how do we tell if it's towed in or towed out? Well, what we do is we put a big straight edge against the main wheels. Then we can use a carpenter square. Now, once again, I'm going to say, here is forward. Okay. So when we do that, right here and right there should make contact if they are
Straight.
neutral, if they're straight, okay? If, for example, it hits the front of the rim, but not the back, then it's towed out. If it hits the back and not the front, it's towed in this case. Make sense? If not, I'm okay.
Do they not use lasers at all? Do you know how
Oh,
to do
no.
it on cars?
No. Generally, not too much, no. And I mean, we're not like worried about the caster. We're not worried about that. We're not, It's like, hey, is it straight? Yep, good.
All right, no problem.
Oh, no, sorry to say, car suspension system is much more complicated. All right, now, there's also, like if it's a fixed geared aircraft, there is no torque links. So how do you adjust the tow in, tow out? Well, where the axle meets the landing gear, the spring steel, this is where shims could be used to then, which are little wedges, to then tow in and tow out the tire. But keep in mind, unless once it's done, pretty much it's a fixed landing gear, it's fixed. So if you find that you're getting tow in, tow out, that's out of limits, it's generally not, hey, let's adjust it by adding or removing shims anymore. It's something has gone wrong with the spring steel, and the landing gear has to be replaced.
Mm.
Yeah. But the shims are generally done at the very beginning. Okay. This again is where we have the torque links and where it says place washers here for adjusting tow in and tow out. Okay. Now, what we also do, and on a lot of aircraft, okay, especially the more rigid landing gear, meaning spring steel in that, the weight of the aircraft can put enough friction on the tire that we get an improper testing, or checking or an inspection, because the friction between the tire and the ground is keeping that tire not going to its natural position. Okay, so what we can do is use what's called grease plates. So taking two pieces of metal plate, putting grease between, we move the aircraft onto the two plates, and then we move the aircraft back and forth, and this will remove the friction between the tire and the ground and go into its testable position. And then once again, this is showing the checking of the tow in and tow out. And the same goes with the camber, okay? As I said, with the camber, a positive camber is when the top of the wheel leans outward. A negative camber is that the tire is leaning in towards the inboard, and that's the top of the tire, okay? Now, most, say, rigid or spring steel or fixed geared aircraft, the only adjustment would have been initially with the shims, okay? Other than that, there is really no adjustment at all. With an oleo strut with retractable geared aircraft, and what we have is what's called a drag link, a part of the gear that pulls the gear up and down. And generally the drag link is what you would adjust to get to the neutral camber. Because most of the time we're not looking for positive or negative camber and such. Why? Because we are set up to go and take off and land straight. So we want everything to be like neutral toe, neutral camber, you know, straightforward, in line with the longitudinal axis. Whereas I know people with cars, depending upon what you're doing to increase or decrease the handling capabilities, you know, there's a lot more things that can be done. All right.
Is there any situation where you would want
No.
other than neutral?
Nope.
Okay.
Well, okay. Going back, spring steel. You know, now this is without the weight of the aircraft, right? But we can see how it has a positive camber. You know, now it's theoretically, you know, that, okay, at a specific weight of the aircraft, you would have neutral, okay? But these aircraft were not really too concerned with how much camber does it have. Because they're spring steel, they will definitely have a positive camber. If they don't have a positive camber, once again, we have a problem with the spring steel gear, not say the tires or the rims and axles and stuff like that. Now, what's kind of crazy on this is a lot of flight trainers have this. Can you see that when the pilot comes into land, we're actually hitting the outboard portion of the tires first?
Yeah.
And that part of the tire wears very, very quickly then. So much so that you don't get very much life out of that tire if you do not rotate the tires. When I say rotate the tires, we don't mean taking the left tire and putting it on the right, because if you take this tire, put it on this one, the same wear pattern is going to happen on the outboard. So what we would do is actually, once the tire shows a little wear, right, we then remove, disassemble the tire and flip the tire itself onto the rim so that the unused portion, you know, the inboard, is now the outboard.
And when that plane is on the ground, that camber is neutral, right?
Well, depending upon the weight of the aircraft, because, you know, how do I say it? If you had, let's say the aircraft, and I'm just going to choose a very small aircraft, like a 152. Okay, it's designed to carry 2 passengers and full fuel, let's say. So that's where you would get the neutral camber.
Okay.
Oh, if you're now one person with a half tank, it's not as heavy, and thus it would have more of a positive camber.
Okay. Makes sense. Thank you.
Yeah. All right. We're going to take our break at this time, and I will let you know that we're really close to being done. Okay. We're going to go through the aircraft retraction system, okay, for small aircraft and large, but we're going to go through that. And then I'm just briefly going to be talking about brakes a little bit. Well, I probably won't, because no. We just got a little bit more to go. But meaning just a few pages, but it will take a little bit of time. So I don't want to just blow right through it. So we're taking a break. We will be back in approximately 10 minutes. All right. And then we'll finish up the lecture for the day. Good?
Okay. Mhm.
Bob's on break.
Okay, cool.
Okay, folks, to continue on. Here we have a small aircraft retraction system. And it's a hydraulic system. And the situation that we have is this. When you go to airframe 2 next turn, you go through hydraulics. So for landing gear, we kind of go over how the system operates, but we're not going deep into the hydraulic power pack, the actuators and such. Just kind of an overview of really how the system works and the purpose of the different components, but not physically how each individual component kind of works. Sorry to say. So in this small landing gear retraction system, now understand that there are many different types of landing gear retraction gear systems. This one is known as a hydraulic power pack, in that the aircraft does not have a hydraulic system by itself, per se, to operate, say, flight controls, flaps, and different things. So many times, this is a system that is common on very small aircraft, be it Cessnas have a similar system. This one is more representative of a Piper aircraft. But even large aircraft, the system basically works the same, okay? And so let's begin. All right, to keep it simple so that we can understand, all right, we have 3 actuators. Basically, they're cylinders with a piston. If hydraulic fluid goes to the bottom of the pistons, it pushes the pistons up, which then retract or pull the gear up through mechanical linkages. If the hydraulic fluid is pumped to the top of the cylinders, the actuators, then the gear comes down. Okay. Now, this yellow box is known as the hydraulic power pack. A hydraulic power pack is a self-contained unit that has a reservoir for the hydraulic fluid. So that's where the hydraulic fluid is stored. It has a pump and it has an electric motor. So when you turn on the electric motor and say, for example, a gear selector switch, when you select up, the hydraulic pump is turned by the electric motor, and it's going to pump hydraulic fluid here and to the 2 main, but you can see that it's pumping it to the lower portion of the piston that then is going to retract the landing gear. All right. Now, that's weird. Okay. So, and then once again, if the pilot was to select down, then what happens? The pump pushes the hydraulic fluid out this way and goes to the top of the cylinders, and thus the landing gear is extended. Now, in this case, once the gear selector is up, the hydraulic fluid pumps to the cylinders and starts retracting the gear. Now, what holds the gear in the up position is hydraulic pressure. And understand that when the pistons are moving, the pressure is not really increasing at all for the fact that the piston is moving. But once the gear goes to its full travel, then we have this device here called a pressure switch. What will happen is the hydraulic pressure in that line is going to go up and activate the pressure switch. The pressure switch then will turn off the power pack, meaning the electrical power going to the power pack. And then that's shut off and the gear is held up by the hydraulic pressure. Are we clear on that? It's that simple. Okay. Now, one thing that can happen is we can get a leak within the system. Okay. And there are two types of hydraulic leaks. There's external leaks and internal leaks. An external leak is that, for example, one of the connections to the hydraulic cylinders are loose. So hydraulic fluid comes out. An internal leak is basically if one of the O-rings on the pistons goes bad, then the high pressure hydraulic fluid can bypass the piston and return back to the power pack. So during a landing gear retraction test, or let's say a customer comes in and says, hey, when I'm flying, I hear the power pack cycling on and off. What that is that what's supposed to happen is the gear's retracted, the hydraulic power pack is shut off, and until they lower the gear, they should never hear the power pack turn on. Now, why would the power pack turn on? Well, if there's an external or an internal leak, the system pressure is going to drop and the pressure switch is going to turn on the hydraulic power pack once again to raise the gear up fully and to increase that pressure. So to diagnose this, what we would do is bring the aircraft into the hangar, jack it up according to the maintenance manual, and do a gear retraction. So we bring the gear up and then we turn the power off and then we wait. Now, if it's an external leak, what we're then inspecting for is any signs of hydraulic fluid leaking from a line and actuator. You know, many times you will see it on the aircraft, it will start dripping and stuff. And then we locate that drip or that leak, and then we repair it as required. Now, external leaks are generally much easier to diagnose than an internal leak. But if it's an internal leak, let's say it is the left main actuator that has an internal leak. Well, what generally will happen is we won't see any hydraulic fluid externally, but the left main landing gear will start to slowly extend outward. And that's a very good representation that that actuator is bad. And thus some actuators we would then be able to remove, replace with a new one, or disassemble, excuse me, or disassemble and repair properly, okay? And then once we do that, we put it back in and we test it once again. And that should solve the problem, okay? And that's basically the pressure switch and internal, external leaks. Now, we also see we have this device right here, and it says it's a thermal relief valve. And that's kind of a misnomer because although, well, let me just try to explain. All right, what the thermal relief valve does and what it really is a pressure relief valve. The problem is that we have the hydraulic fluid trapped. And as we said, we cannot compress a liquid. But the problem is, let's say that it's kind of a cool day at one point. The hydraulic pressure's 1,000 PSI, right? But it's trapped. Now, if the temperature of the hydraulic fluid rises, what happens? It wants to expand because hydraulic fluid will expand and contract with temperature, but you can't compress it. So if it just rises slightly in temperature, the pressure will go up significantly. So much so that if we have a good enough rise in temperature, it could actually exceed the bursting pressure of the lines, the fittings and such. So the thermal relief valve relieves the extra pressure caused by the thermal expansion of the fluid. That's why they call it a thermal relief valve. Okay, so if the pressure goes up too much, let's say the maximum is 1,000. Okay, if it hits 1,100, 1,200, what happens? The thermal relief valve opens a little bit, because basically all it is a ball and a spring, and as it will release some fluid back to the reservoir. So the thermal relief valve, the high pressure is here, it goes through the valve and gets returned back to the hydraulic power pack reservoir. And that's the thermal relief valve. The next little thing that I want to show you is on the nose gear, they have a restrictor here and a restrictor on the inlet, you know, the up and the down, okay? The restrictors, many people will say, is to reduce pressure, and it's not there to reduce pressure. It's actually there to reduce the flow of fluid to the nose gear actuator. Now, this is a, what? Sorry, I don't know why it's not centered. Okay. All right. Restrictors are used to control the rate at which the landing gear comes up and down. In this case, let's say we want all the gear to come up and down at the same rate. And understand that each aircraft is designed specifically for that make and model of aircraft to have the gear come up a certain way. Some aircraft, the mains and the nose come up and down at the same time, but in some cases, the nose wheel might come up faster and extend faster than the mains. Some, the mains go before the nose gear. And this all deals with the aerodynamics of the aircraft, the weight and balance of the aircraft, and ultimately the control of the aircraft, okay? So whatever they find or is necessary on how the gear comes up and down, this is where the restrictors can be used to get what we want, okay? Because the restrictors reduce the flow of fluid. And I'll give you an example. Out of 100% of the fluid flow, notice that we have a junction here. Now, we could say that 50% of the fluid goes to the nose gear and then 50% goes to the mains. But at this junction now, the left main only gets 25 and the right main only gets 25%. So could you see that that's 50, not 30? Okay. Could you see then the nose gear without restrictors would go up as twice as quick as the mains? And if we wanted that to be more equal, the restrictors would be in place to reduce the flow. So now, say 30%, 33% comes here, 66% comes here, 33, and then 33, and thus that's the purpose of the restrictors. Keep in mind, the restrictors in a landing gear retraction system is for timing of the gear. Okay. Next. Okay. Next, we have what's called a free fall valve. Okay. Here is the scenario. The aircraft was designed with no free fall valve, okay, or any type of an emergency extension system. And keep in mind that any aircraft that has a retractable geared system has to have an alternate way than the standard way to extend the gear. Not necessarily to retract the gear, but just to extend the gear. So if this did not have a free fall valve, what would happen? Let's see. The gear is retracted, but during flight, for whatever reason, we had an electrical failure or a hydraulic power pack failure. Okay. Well, then when the person wanted to place the gear in the down position, the hydraulic pump's not going to work, the valving ain't working, and thus the gear could not be extended. So to solve this problem, they installed what is known as a free fall valve. Keep in mind, when the landing gear is up, it's only being held up by hydraulic pressure. So we have a high pressure here, but we have a low pressure on the opposite side of the free fall valve. And remember, the fluid wants to go back to the reservoir of the hydraulic power pack. So in this case, if there was an emergency, say a failure of the hydraulic power pack or an electrical failure, the pilot could pull out the free fall valve, releasing the high pressure hydraulic fluid that's holding the gear up, and return it back to the power pack. We use gravity, the weight of the wheels in the landing gear, to then drop down to the fully extended position. Okay, so that's the emergency extension system for that. Now, there's more. Okay, well, Piper, and it was very famous early on, Piper decided, well, sorry to say, but a little story. Remember, this is kind of on small general aviation aircraft, and there's a problem. We have people called pilots that fly these airplanes. And when they first learned to fly, most likely they've flown a fixed geared aircraft. Then they bought an aircraft, for example, this type of aircraft with retractable gear. One of the things that pilots would forget is to follow the checklist. And so they would come in and they would forget to lower the landing gear, and they would do what's known as a gear up landing. And go, oh my God, I just, wrecked the aircraft. I forgot to put the landing gear down, blah, blah, blah. So Piper came up with an airspeed sensor for an automatic extension system. What this did was, when the aircraft went below a certain speed, and we'll say 120 miles an hour. Well, at 120 miles an hour, the gear would be extended through the free fall valve. So we have this airspeed sensor. Basically, we have a diaphragm. Sorry.
I'm
We have a
guessing.
diaphragm. Okay. Now, this is connected to the pitot tube and the airspeed sensor. Okay. So when you're going faster than 120 miles an hour, the impact pressure pushes the diaphragm to the left, which closes off the free fall valve.
Okay.
When we go slower than 120 miles an hour, the air pressure is not great enough, and the free fall valve is now opened. It's a very simple but effective system. Okay. So how this was supposed to work is this. If the pilot was coming into land but failed to put the gear in the down position, once they went below 120 miles an hour, the airspeed sensor would pull the free fall valve open, releasing all the pressure that kept the gear up, and the gear would do an emergency extension to the down and locked position. And the pilot could land. Yay, right? Well, the problems started to exist. One, pilots learned, hey, why do I have to move the gear handle anymore if I have an automatic extension system?
Oh, no.
Yeah. So
My
some pilots, what they would do is leave the gear selector in the up position. Now, they start the aircraft, they're on the ground, they're taxiing. They're not doing 120 miles an hour. So the pump is running, but it's just circulating. Okay. Now, when they go to take off at 120 miles and they leave the earth, they're doing 120 miles an hour, the free fall valve is closed, and the landing gear is retracted. Hey, we come in, and the gear automatically extends when we're below 120. Sounds really good. Okay.
No.
Well, there are situations in which we want to fly below 120 miles an hour, but we don't want the landing gear to automatically extend. So they added a lockout to the free fall valve. Okay. And this is for what's called minimum controllable airspeed. For example, when you're practicing flying in that, you're supposed to do what's called minimum controllable airspeed, meaning fly really slow, but keep the gear up. If you needed to do a water landing, you generally want the gear to stay in the up position.
Yeah.
Well, the automatic extension system wouldn't allow you to do that. So they put a lockout. Well, pilots would, like leave the gear up position, but then they're doing the minimum controllable airspeed, and they would then lock out the free fall valve. Well, when they come into land thinking, hey, I don't need to lower the gear because the automatic extension system will work, but they never undid the lockout, and thus they do a gear up landing. Okay. Next, what they also found was that eventually the diaphragm will get a leak in it. Okay. So let's say it's supposed to extend the gear at 120. Well, if the diaphragm gets a leak in it, now it might take 140 miles an hour to keep the gear in the up position. Once you fly less than 140, the free fall valve opens. Well, that can cause additional problems aerodynamically, but some landing gear you can extend above a certain airspeed. And 140 miles an hour might be way too much for this landing gear to handle, and thus extend out and fail. So guess what the FAA came up with?
Like a horn? Oh,
No, an AD says you have to disconnect and remove the automatic extension system.
so
Yeah, there was so many problems and stuff like that, that pilots relying on it too much and such. And then with the diaphragm leaking and the gear extending when it shouldn't, blah, blah, blah. They're like, okay, any aircraft that has this airspeed sensor for automatic extension must be removed and disconnected. Okay. Now,
Why wouldn't they link it to elevation instead of airspeed?
well, because elevation, understand that we fly by, how do I say this?
elevation.
That would work for like North Perry Airport because we're basically at sea level. But when you're flying, for example, if you're out in Denver and you land, if you look at your altimeter, it could say roughly 5,000 feet.
Yeah, because it's
Okay,
Every
yeah,
airplane's
that
at a
makes
different
sense.
elevation.
yeah, that's-
Now, a lot of aircraft now have, what's called a radar altimeter, which basically sends a signal like a depth finder of a boat and says, hey, you're above the ground this far. But we're talking cheap old technology here. I'm sorry to say it's still out there.
yeah, it is.
All right, that makes sense.
Yeah. Now, but that's really the hydraulic power pack system. Once again, it's a self-contained unit. Cessna, Piper, a lot of small general aviation aircraft use it to raise and lower the landing gear. I've seen aircraft that have mechanical systems instead. One, which was crazy, was it actually looked like an emergency brake handle inside the cockpit. And it was totally mechanical in that you pulled up on the handle and you retracted the gear. You pushed it down, you extended the gear. Other aircraft I've seen with electric motors with chains and sprockets and a gearing system that just cranked up the gear that way. Our Cessna 310 uses push-pull rods, no hydraulics, uses a transmission that pulls and pushes the gear into the up and down position. It's just, there is a lot of different ways. Now, a lot of large aircraft, they use hydraulic systems because of the mechanical advantage. And really the only difference is that instead of having a self-contained hydraulic power pack, these two lines are basically connected to the hydraulic system of the aircraft itself. And the aircraft has a hydraulic system, and large aircraft have multiple hydraulic systems to run the systems. Be it the landing gear, the flaps, the spoilers, the rudder, the elevators, and such. Are we good on that? Yes, no?
Yes.
Okay. All right. As I said, all landing gear that are retractable have to have a means of extension, an emergency extension. Most aircraft use gravity, because if gravity fails us, you don't have to worry about hitting the ground, because you'll never land. But gravity works the best, So usually the emergency extension is whatever is holding the gear up is then released, and the gear falls down to what's known as the down and locked position. Okay. And I will discuss what the down and locked position is when we're looking at the landing gear and inspecting the landing gear, because generally they use what's called an over centering switch, safe locking device. Now, large aircraft retraction systems, the big difference, I would say, is that once the gear is in the up and locked position, it's not hydraulic pressure that keeps the gear up. Large aircraft, we're dealing with thousands of PSI, 3,000, sometimes even higher. And so they don't want to try to keep that pressure on all that equipment during all the flights, during the whole flight. So they will have mechanical locks that grab and hold the gear in the up and locked position. And then there's ways that those mechanical locks can be disengaged so that gravity can take over to extend the gear. All right. So now we go into the landing gear safety devices. The first one that we have is what's called a safety switch. Okay. Let's say that's brakes. All right. It's called a safety switch. Okay. Now, a safety switch is usually installed on one of the landing gears. Generally, it will be the left landing gear, but it doesn't always have to be. And what it is if the aircraft's on the ground, this safety switch is activated to prevent the landing gear from being inadvertently retracted. Because it senses the weight is on the wheels, some people call it a WOW switch, meaning weight on wheels. The official name is safety switch, but many people call it a WOW switch, weight on wheels. Some people even call it a squat switch. Why squat? Well, when the aircraft's on the ground, the weight is on the oleo strut, and it looks like the aircraft is squatting somewhat. So squat switch, by the way, that's what I grew up with, is being known as a squat switch. Other people, WOW switches, but really it's a safety switch. Now, pretty much when the oleo strut is compressed, it activates the safety switch and thus prevents the landing gear from being inadvertently retracted. When the aircraft takes off and the weight is no longer on the wheels, then the safety switch can re-energize or make the landing gear retraction system operable. Now, very similar, I had a customer, he had a twin engine aircraft, and he would brag about like, oh, Bob, did you see me take off? And I'm like, no, I didn't really pay attention. Why? He goes, oh, my landing gear comes up really quick. My trick is I put the landing gear in the up position before I take off. I'm like, okay, why do you do that? Well, that way, as soon as I'm off the runway, my gear comes straight up and it's great, blah, 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 blah. I'm like, okay, who cares? Like, who cares how fast your landing gear or how fast you retract your landing gear? But he would leave the switch in the up position. And then when he came into land, yes, he would put it in the depth. Well, one day we got a call, and what happened? He was leaving Orlando, and he did his famous little trick. He put the landing gear switch in the up position. He started running down the runway, and his airplane kind of hit a bump, and he went a little bit airborne for a second, which then allowed the landing gear to be retracted. The only problem is the aircraft settled back down, and both propellers hit the runway. Now, he did not crash. He was able to recover, and he still took off and circled back and landed. He called us and said, hey, I have this problem, blah, blah, blah. And I told him, okay, you had an impact of the propeller, but not a sun stoppage. So what you need to do is both propellers have to be removed and sent out for overhaul. You have to overhaul the propellers. And then whoever you get the work done, they have to do what's called a run out check on the crankshaft of the engine to make sure that nothing is bent.
Yep.
And so that little lifting up that handle for takeoff to be cool cost them probably $10,000 for the propellers themselves to be overhauled, $5,000 a piece, plus removal and installation, do the run out check on each engine. By the way, the engines were fine, just needed to overhaul the props. But still, it probably cost them between $10,000 and $14,000. And that was many, many, many decades ago now. So that would probably cost them, $25,000, $30,000 in today's dollars. Yeah, it's like, folks, don't try to make shortcuts. Just do what you're supposed to do, follow the procedures.
Yeah, I hate that, because what if he had an engine failure on takeoff and then his gear is up?
Oh, and people do weird things. Anyways, that's the safety switch.
Wow.
Next, we have landing gear safety pins. Okay. And I don't have a picture of one. Okay. But in your textbook on top of page 917, and we will look at that also, but it's a mechanical pin that locks the landing gear in the down and locked position. It's generally used when the aircraft's on the ground being serviced. We lock that out because we don't want anybody to certainly retract the gear when the aircraft's on the ground or somebody's working in that area. So it's a mechanical device. Okay. We got gear indicators. Now, with the gear indicators, the FAA says that, like, the actual regulation is when the gear is down and locked, you shall have a visual indication that the gear is down and locked. Okay. What this could be as simple as a single green light for only one light indicating that the gear are down and locked. Now, most manufacturers go above and beyond this, because if you only have a single green light, if the green light's not on, yes, you know that the gear are not down and locked, but you don't know, are all of them not down and locked? Are two down and locked, but one is not? And if one is not, which one? Because if you're coming into land and you don't have an idea of which gear is down and locked and which ones are not, or vice versa, for example, if you have a left gear that's not down and locked and you know that it's not down and locked, what do? You land on the right wheel, you hold it back, try to get the nose to touch, and then you fall on to, say, the left landing gear. If you know the nose is not locked down, then there's a different approach to that. So most manufacturers will put a green indicator light for each gear, for nose, left, and right. Okay, that if they're down and locked, that perspective light will be green to indicate down and locked. Some manufacturers even go further. And so I'll just jump to the ultimate. Some aircraft have 3 green to indicate that the 3 landing gear are down and locked. They have 3 red lights indicating that the 3 gear are up and locked. And if not, which one is not up and locked. And also have what's known as a transition light, meaning that the gear is not down, nor is it up. Yeah, so that's generally will be the most that they'll have. Okay. Now, there's actually a famous accident that happened over the Everglades here back in the 1970s. And that is an aircraft. I don't know if it was coming from New York or not, and I don't remember if it's Eastern or Pan Am that it occurred. But what happened was, and what you have to understand is that in the 70s, the pilot of the aircraft was, how do I say, was the commander. You could not argue, you were to question the captain of the aircraft. What they said went. And so it was a very, very military type of
Structure.
command, yeah, environment. So anyways, they were coming into Miami, and as they lowered the gear, they found, I believe it was the right gear, green light did not come to show that it was down and locked. So the captain called Miami Tower and said, okay, we have a problem. We're going to go into a holding pattern, which means they basically were flying at, I don't know if it was like 5,000 feet, 2,000 feet, but they were set at an autopilot altitude hold just to fly in circles, okay? To try to figure out what was wrong with the right gear. They cycled the gear up and down. Now, this was a 3 manned aircraft, meaning you had a pilot, a co-pilot, and a flight engineer. What the captain failed to do was to assign somebody to keep a watch on the aircraft itself. Well, they're playing around, they're moving around, and what supposedly happened was that the captain hit the yoke and it knocked it out of the altitude hold position. I'll describe it this way. Many of the aircraft have what's known as altitude hold, where then you say, okay, I want to fly at 3,000 feet. As long as you don't touch the controls, the aircraft will maintain a 3,000 foot altitude. Very similar to your cruise control on your car. You can set it for 60 miles an hour and it will try to maintain 60 miles an hour. Now, what happens when you tap on the brake?
Cruise control and
It shuts off the speed control. Okay. Well, the same thing happens with the yoke. The pilot hit the yoke, thus the altitude was shut off, but it still maintained the circular path. So the aircraft started to slowly descend. The air traffic control noticed this and actually called the aircraft and asked, was everything okay? The captain got really, really mad at the control tower for questioning what he was doing and how he was doing it and stuff. So back in those days, that's, it was like, okay, captain, sorry. And just watch the aircraft spiral into the Everglades.
oh,
Yeah. Now, you want to know what's crazy? Anybody ever hear of this accident?
no.
Okay. What they discovered was that the gear was down and locked, but the right landing gear light bulb, meaning the indicator light bulb, was burned out.
Fudge.
And what's crazy about that is for the pilots to be able to check the light bulbs to make sure that they're working, there's what's called a press to test switch. So on that type of aircraft, all you had to do was push the landing gear light in, and that would illuminate the light bulb temporarily to indicate that the light bulb is functional. They did everything. And even on that aircraft, there's what's known as a hellhole that the engineer went down into to visually look to see if the gear was down. And when he says that, because he actually survived, he said, yep, I seen the landing gear down, but then I seen the Everglades, and that's when we hit.
Oy.
Yeah, some people died, some people survived, but it's not a good thing. And we've already talked about nose wheel steering or nose wheel centering. Okay. I got a pet peeve on nose wheel centering. Okay. I'm going to tell you what the FAA wants. One of the FAA questions talks about, like, on a retractable landing gear, why is there a nose wheel centering? And it says so that when the gear is retracted, it will go directly into the nose gear, so that it doesn't jam up. That's not fully wrong, okay? But what I don't like about it is that it says centering. And yes, it says retractable. Why is it centered? Well, I've seen a lot of retractable geared aircraft that when the gear is retracted, it's not centered, meaning it could be rotated, it could be at 45 degrees, it could be this, it could be that, however it needs to be to go into the wheel well area. Our aircraft, the 681 that you guys worked on with the door and the window, the main gear actually turn 90 degrees before they go into the wheel well area. So is that centered? That's a play on word. Well, it's centered properly in the wheel well, so it turned at 90 degrees. Yeah. I always look at it. So for FAA, it's for when it gets retracted, that it fits into the nose, into the wheel well area. Okay. But all steerable nose geared aircraft have a centering device. And what is the reason for the centering device? I talked about it when we did the rudder for the nose wheel. It is so that when you come into land, the nose wheel is straight, because you don't want to lower that nose wheel doing 100+ miles an hour and it's going to make a sharp left or right turn. You want it to be centered, and then once we can press the oleo strut, the weight is on the wheels, that's when we have control of the steering. Are we good with that?
Yeah, that makes sense to me.
Yeah, I hate that FAA question. Really, that's really it for the lecture for today on Section A. All right, I'm going to stop the recording